So this is like a border. Everything what is inside belongs to the state. Here is the state with the boundary. Yeah? Here is the boundary itself.
What would be the Polish term?
Granica. Jack.
A to jest skala delta, ten symbol?
Yes, it's delta. Okay, and that's the boundary.
And in real map of Europe, what you draw in green would be England, for example, the open boundaries being
yeah.
in Scotland.
might be, yeah, that's right, yeah.
I'm sorry, in the terms of interior and the exterior, the boundary would be the same if the set is closed and open. Just looking at those two pictures, yeah?
Yeah, the boundary would be the same in those cases.
But it doesn't matter whether the set is open or closed.
Yes, it doesn't matter. Sometimes it does, sometimes not, but generally speaking, when you want to count the boundary, what you do, you take something a little bit bigger than a set, which is A. There is something that bounds the set from outside, and then you try to take out from this a little bit bigger set everything which is inside. So everything that fills this set from inside. So this set, you can embed this set here, you can embed it here. Or you can also embed this set here, and you can embed this set here.
So in that light, in that light, it makes, for me just, it makes sense when the set is bounded, but when it's not bounded and you take the interior and the exterior defined that way, I don't grasp this idea of being unbounded. So what exactly it is? I don't think of the space in between. Because this kind of a definition fulfills everything, and gives like the very impact of the border here.
Yeah.
But how does it go with what is unbounded?
Here. Or here.
Here. Let's compare this part and that one. So if you define it with the tools of interior and closure, then the boundary is here vivid. Here it's not vivid because it's unbounded. But if you apply this interior and that closure into that one, it becomes vivid, but it's unbounded simultaneously. So how? I don't know if it was quite clearly.
I don't know, but what the boundary says, it says about all the parts of this set which are on the border of this set and the exterior of this set.
Mm-hmm.
And actually, from the perspective of the boundary, it doesn't matter what is bounded in this set and what is not bounded. Because this set, this set, this set, and this set have the same boundary. All those four sets have the same boundary, and it is this.
Mm-hmm.
So boundary is not to measure what is bounded and what is not bounded, but rather trying to say where are the limits of the set. Where is the point where the set meets external space? This is the boundary. And it meets the external space here, where it is not sharp enough, but it also meets the external space here, where it is sharp. But in those both types, where it meets the external space,
okay.
It's
So how can you distinguish bounded and unbounded sets only in the terms of interior and closure?
okay, so a bounded set is a set which is, in this sense, bounded set. But I wouldn't call it bounded, actually, because you call it bounded in an intuitive sense. But in topological sense, I would say it's closed set. A closed set is a set that says boundary.
So how would you distinguish closed and open sets only in the terms of interior?
Yeah, exactly. So closed set equals its closure. A is closed set when A equals its closure. And A is open set when A equals its interior. That's how I distinguish those things.
Those are biconditionals.
Excuse me?
Biconditionals.
Yeah.
But if you say that interior, I'm sorry to asking so much, just read what try to understand. But then you say that interior and closure fulfills everything, so there is no difference between the definition A and B.
No difference between this and this?
Yes, if interior and closure fulfills all the space, let's say, or all everything what you want to define, I don't really see the difference between this first approach and the second one.
Yeah, this is from outside,
Yes.
and this is from inside.
Yes.
That's the difference.
Okay.
Yeah, these are dual, yeah, but
No.
yeah.
Maybe if we consider a closed set as when you close it, we add all the borderline cases to A. So borderline cases are like we don't know they belong to A or not A, and here are that. And then when we close the set, we add all them to A to the set, and so there it is closed. And then what we do with closure also is like it's the smallest closed set that we add all these borderline cases. So if the set A contains all the borderline cases, already it's like when so the closure would be A itself, because already all of the borderline cases are in A. Okay.
This is obvious because it had been explained for the last 3 hours. I think I'm understanding. Okay.
So borderline cases is when we close A.
I know that.
Okay, and then so we add all these borderline cases to A, and then also consider complement of A, and then we close it also. So we add all borderline cases to complement of A, and then we look at these two whether they have an intersection
Can
or
I
not.
draw something? Maybe you can be clear. So what I was thinking about is that maybe that I can do so that interior, let's say this is doesn't make sense that one and extra closure, yes? Can it be that way defined?
Whoa.
That not everything what is not here is there this way. So everything what is not there is here. So that would be the closure, and made in that way. Yes? Does it make sense?
I don't know what it means. This I don't know what you mean by that.
So that if this is like a topological space, yes, what we want the defined topological space where we want to make an object, yes.
Yeah.
So this would be like a one case. This would be like, let's say, the other one, yes.
Yeah.
So this is the interior of one. This is the interior of second, and this is the exterior of one, and this is the exterior of second. So A plus C fulfills all the topological space here and here, yes, am I right?
Yeah, but C, in this sense, C is not a closure.
This, why? So then this and this one.
Yeah, because closure is if you have this, the closure of this looks like that. This is the closure, not something outside of it.
But this one should equal this one.
Yeah, if you close it, if you count the closure, then you become this.
I mean, not okay, not the terminology.
It's complement. It's not.
Okay,
closure
this
complement.
one is, let's say, this is bounded. This is unbounded.
Yeah.
Yes. So here, with the case of bounded and the unbounded, the same as interior and the same as closure. Yes.
Yeah,
So
but it's not here. It's not here. It's like. Yeah, I don't. Yeah, okay. Let's say I understand. Okay, let's say I understand.
I think I'm. Just talking about the very border, you know.
Yeah. Okay. So what is the
No.
remark? Yeah, maybe we can, I don't know, maybe we can consider like more examples. Maybe that will help somehow. Let's say, let's get back to this example of real line and rational numbers here on the real line. Yeah, so rational numbers. And there are like infinitely many rational numbers, and they are dense here. I don't know if you're all familiar with this notion of rational numbers. They are numbers which have the following form. Q. Yeah, so these are rational numbers which you can present as two integer numbers, one divided by the other. And so this set is everywhere. One can say that it's everywhere. And let's say, can you say how would an open set in Q look like? Can you give an example of an open set in Q? Because we know how open sets look like R, like in real numbers. We have like an open set. It looks like that. It's, for example, an interval from A to B, which is open on both sides. And how an open set will look in the case of Q?
What do you mean as a subspace?
As a subspace, yeah, because Q is a subspace of R. There was a definition of a subspace somewhere here. Yeah, this is the definition of a subspace. So let's say, yeah, so how would it look like, in your opinion?
The open subset?
Yeah, the open subset of Q.
Maybe from square of 2 to square of 5.
Square, yeah, let's say square of 2 to square of 5. And is it open or closed on both sides?
It's open.
Okay. Very well. So why is this open? Because it's an intersection of an open subset of the real numbers and a subspace. So this thing is an intersection of Q. Let's call it A. Okay, let's call it set A. A is equal the intersection of Q with an open subset of real numbers. Yeah? So it's exactly of this form that we have here. Yeah, it's exactly of this form, right? So we take the subspace, we intersect it with some open subset from the big space, and we get an open set. Open set in relation to the subspace. Very good. And a closed set, how would look a closed set in Q?
This one.
Closed. Yeah.
This one is closed.
Yeah. So it's the same, but we use it closed.
No, even without that, this
because
open interval is closed because
Okay.
because the complement of that is.
Okay.
Because this example is very special kind
Yeah.
because you take two rational numbers, so it's both open and closed.
Yeah.
It would be better example with, for example, 1 second, 3/4.
Yeah.
Because you could differentiate between the intersections.
Yeah, but it is important to get such monstrous Klopen sets that are Klopen and open that usually escape our intuition. So this space Q is topology, a topological space with many Klopen sets.
Yeah. So a Klopen set, yeah. If we are at this point,
It's an artificial word from
a Klopen set. Yeah, but it's defined in books, right? So a Klopen set is a set open and closed at the same time. Yeah, so that's a Klopen set. And this example that you gave, yeah, it's a Klopen set, yeah, because it's closed and open at the same time. So now, let's keep to this example. Okay, we have this set, and can you say what is the interior of this set? Yeah, so can you say what's the interior of this set? Okay, the interior is the sum of all subsets which are open. So what is the best example of an open subset in this set? Yeah, the set itself. So when the set is open, as we said here, then it's equal to its interior. So the interior of this set is the set himself. Yeah? And how about the closure of the set? What is the closure of the set? The set itself. Because it's also closed. And when it's closed, it's equal to its closure, right? So the set is close is equal to its closure and is equal to its interior. So what is the boundary of this set?
Empty.
It's empty, because the boundary of the set is closure minus interior. And when closure is equal to interior, then it's empty set, right? So, and it's a general rule that if you have a Klopen set, Klopen sets are exactly the sets which have empty boundary. Okay. Okay. So that was the example. Ah, yeah, there is one more. Yeah, one more definition that I would.
So,
Yeah.
does it mean, I'm just coming from the beginning, so this R is defined like the, let's say, all the irrational numbers fulfills this space, yes? What would we have another definition? That, so would it be the same that if we define it like the sum of everything, would this not be irrational number?
Once again, please.
Because the definition here is that the sum of all irrational numbers give the whole set, yes? Here.
Yeah.
So what if we define it the other way around? Would it be still the same? That this is all what is not, I mean, all numbers which are not irrational.
And what is this? All the time not rational?
All the numbers which are not irrational, would it still be the same?
Yeah, I mean these two objects, I mean rational numbers and irrational numbers, from topological point of view are dual. So they behave the same as subspaces of the real life.
So then, in topological terms, there's no difference between that with the scalar number and the other way. If we want to define all the space and put them together, I mean
there is no difference. I actually there should be a difference because one of those sets is countable and the other is uncountable. So if
one is made of pure negations, I mean from the philosophical point of view, and one is made from pure affirmation. So in the reality, it would be exactly the same reality if it's defined by all the points which are affirmative and from the points which are all the negations, because philosophy couldn't, and here it looks as if it could.
Well, the problem is that it is not a symmetrical situation, because you have rational numbers and you can define irrational numbers. You could do that as not rational real numbers, right? The problem is that there are countably many rational numbers and there are uncountably many real numbers.
Yes.
Which means that when you kick out the rational numbers, you will be left with infinitely, uncountably many irrational numbers. And in this sense, you cannot have a homeomorphism between them, between rational numbers and irrational numbers, because they have a different cardinal number. And there is no bijection between those two sets. So, and if there is no bijection, then even more there is no homeomorphism between them. Because you cannot even put a bijection between them. So, from some perspective, these two sets play a similar role here, but they are not symmetrical.
That's how I feel. But how can you, let's say, precisely call, say, this difference in the terms of topology?
In terms of topology, that's a tricky question.
I mean, for me, the intuition is quite similar to this one. I'm just focused on this, the very verge of this, what is bounded and not bounded, closed and not closed.
Yeah, you cannot differentiate them using the terminology of interiors, closures, and boundary. You cannot do that.
So there has to be something more.
There has to be something more. To distinguish between them in topological terms, you would have to use sequences and accumulation points of sequences. But at the moment, I cannot say precisely how to do
But
that.
still, I think it somehow cuts the infinity, like it happens with the physics when you got the process of renormalization, and then something like that. Something will be missing. Am I right?
I think that your intuition is very good, but I cannot give you a precise argument at this moment.
They have a nice book on topological counterexamples, where it is shown that the topological space of rational numbers and of irrational numbers are different. If you want to know the authors.
Christina and Sibak.
Exactly.
So definitely there are some ways in which you can see it precisely, but at this moment I cannot give you an example. I can think about it during the break, right? Okay, so just to finish this part, I will just introduce one more word that, one more word. Where is this? If you consider these rational numbers as a subspace of R, and you look at the closure of it, but the closure of it in, let's put it like an index in R, in the real line, so not the closure of this set from the perspective of this set, but the closure of this set from the perspective of real numbers, you will see that you get everything. So the closure of this set in real numbers is the whole space. And it's a very specific situation, and it is called in topology a dense set. So a set which closure is the whole space is called dense. And it somehow relates to the basic intuition of behind the meaning of the word dense. If something is dense, it means that it fills the whole space somehow. Maybe it's not equal to the whole space, but it fills it. It's somehow distributed everywhere. So at every point of this space, you can find representatives of this set. And maybe to show you the very famous dense sets, which are not rational numbers, let's say. No, maybe not. Maybe not. No, because I won't be able to explain it before the end of this part. Okay, so maybe we'll break now. It's like 3 minutes to the break, and then we'll start like at 5 again, okay? Because it's a natural moment to stop. Alright, so let's start. So first I have to admit that I don't have any better solution for you. So I thought about it for a while, and I guess that the only, but on the other hand the best argument is that those sets have different cardinal numbers. And that's enough. But from the perspective of their structure on the real axis, they are almost the same. Okay, so now new vocabulary. Okay, I will tell you what is connected space. Okay.
What about this strange set you mentioned before the break?
Yeah, maybe I will say about it in the end if we'll have time. Okay? Okay, yeah. So just to say what is a connected space. So if we have a space X definition, yeah. If we have space X, and we have A and B elements of X, that's a topological space, and A and B are elements of X, and we have a continuous map. Alpha from from 0, 1 to X such that alpha of 0 is A and alpha of 1 is B, then alpha is called path. And if for every A and B from X there is a path between A and B, then X is pathwise connected. In Polish you say spójna, and pathwise connected is drogowo spójna. Okay. So let's draw a picture as always. So for example, imagine a sphere. It's a sphere, so it's empty inside, okay? It's a sphere, so it's empty inside. And imagine 2 points, A, B, and imagine a path between A and B. Okay. That's a path between A and B. And actually, in the sphere is pathwise connected. Every 2 points from the sphere can be joined by a path. And that's the basic intuition. Yeah? And that's why we say that the space is pathwise connected. Also, I can give you also another intuition here, how you can distinguish objects in the space. Topologicians sometimes also say about something called simple connectedness. So a space X is simply connected if for every closed path, which is also called a loop, which is in the case where alpha in 0 is equal to alpha in 1. Okay? If for every closed path, this path is contractible, which is in Polish ściągalna. And I will give you the intuition. So here is a loop, okay? These are like 2 points. No, there is a 1 point, let's say, and there is a loop. There is a loop, okay? Why it's a loop? Because it starts and finishes at the same point, right? So it's a loop. And what it means that it's contractible, it means that you can think about it as a rope. Yeah, imagine it is a rope, and you try to contract it. So you try to make it smaller, shrink it somehow, and you contract it. And if you have a rope on a flat surface, you can just contract it, and there will be no knot. Yeah, no problem with it. But imagine you have a donut like this one, yeah? And you have a loop here. Yeah, you are not able to contract it. Okay, is it clear, this intuition? You cannot contract it because there is a hole inside. And that's a very basic way in which you can distinguish a sphere from a toroid. You do it by saying that here they are all the loops are contractible, and here there are loops which are not contractible.
This is a hard example. Nice. It took people 100 years to prove it, I think.
Yeah.
Spark-Arrest hypothesis is the first one. So.
That's not that easy, yeah, of course, but here is just intuition. Yeah. Sometimes simple things occur to be very difficult, yeah, to be proven. Yeah, but that's an example. And yeah, for example, okay, that's so that's the, and there is another definition of connectedness, which is not pathwise connectedness, but it is connectedness. So definition: a space X is connected if it cannot be presented as a sum of two open, non-empty, disjoint sets, subsets. Okay. So, for example, a space that looks like this. Now maybe an easier example, okay? An easier example. Let's say, like I will draw it here, okay? Let's say a space that looks like this. It's a flat picture. Okay, we have like two disks which have one. No, they shouldn't have a point here. Sorry. Let's imagine that these are the disjoint. Okay, let's imagine that these are disjoint. Okay, we have like two. We have a set or a space that consists of those two circles, those two disks, open disks. So it is not connected because it can be presented as a sum of those two sets. That's a trivial example, but just to show you that it can be like that. So it is not connected because you have one component and second component of this space, right? And if you have, for example, space that looks like this, which is like single open disk, then it cannot be presented as two sets which are non-empty, disjoint, and open. Okay. If you, for example, cut it like that, then you have to decide whether this line is inside of this set or inside of this set. Yeah? And if you put it to one of those sides, then this side will be closed and the other one will be open. So you will have like a sum of two subsets, but one of those will be closed and not open. So that's the basic intuition. And this is also something that enables us to distinguish spaces by saying that some of them are connected and some are not connected. In most of the cases, pathwise connectedness is the same feature that connectedness. So these are like the same thing. But there are some very exotic spaces where there is a difference between these two notions. But don't mind. Okay, and let me give you a fact about it. So, if fact, okay, if X is connected and F is continuous and surjective, then Y is connected. So it's what it says is that if we have something that is connected and we'll transform it in a continuous way, we'll compress it, squeeze it, stretch it, then it will remain connected. Okay? To make it unconnected, we would have to do something which is not continuous, like cut it or puncture it. And that's a theorem, but I don't want to give you a proof now. Yeah, and to show you how we can, for example, distinguish spaces using disconnectedness, we can consider an example. We can say that, let's see if a real two-dimensional space is homeomorphic to a real space. Yeah? In other words, if this picture is homeomorphic to this picture, let's say. And we can look at it from the perspective of connectedness in the following sense. We can make a puncture here. So like making a puncture inside of this plane. And we can make a puncture here. Okay? And now we see the difference. The difference is that by making a puncture in this object, we end up with something which is still connected. So this space is still connected. Yeah, because if we have 2 points here, we don't have to go through this point to join them. We can choose a path that goes in this way. And in this sense, this space is still connected, pathwise connected. But if we puncture this space in here, then we cannot join those 2 points anymore. Which shows us that these are like 2 different spaces from the perspective of topology. Okay, so that's one thing. Maybe I don't want to go into detail with that, but I will just mention that if you have 2 spaces, 2 topological spaces, like for example this one and this one, then the sum of these spaces is also a topological space. Maybe it seems to be obvious, but it's not completely obvious that you can do that. But yes, you can do that. So having 2 spaces, you can create another space by saying that it's a sum, disjoint sum of those 2 objects. Okay? Because you know we are a little bit out of my planned schedule, so that's why I try to go faster than I planned initially. Okay. Now I will say a few words on product of topological spaces. I don't know if you remember what is a product of 2 spaces. Like, if we have a Cartesian product, so imagine you have 2 spaces, x and y. So you can consider x times y in a Cartesian sense, and it is the set of all ordered pairs such that x belongs to x and y belongs to y. That's the Cartesian product of 2 objects. Yeah? So let's say, just to give you an example, let's say x, it is a set consisting of 0 and 1. And y, it is a set consisting of I don't know, A, B, C, right? So what is x times y? It is a set consisting of the following pairs: 0 A, 0 B, 0 C, 1 A, 1 B, 1 C. Okay? Is it clear? Yeah, so that's simple because we only look at the sets here. But the question is how to define a topology in a product. So we have like 2 sets, we have a product of those 2 sets, and we know how open sets look like in X, and we know how the open sets look like in Y. The question is how the open sets look like in X times Y. Yeah, so that's the question. And so we define the topological space over a product. But to do that, we need first to give the definition of the basis of topology. Maybe here. Okay. Okay, so definition. Let X and T be a topological space. We say that B is a basis of T if every element A from T is a sum of elements from B. Okay, so this is pretty important because instead of thinking about the whole big topology, we can only consider some subset of the topology, and we can generate all the elements of this topology using the elements of this subset, right? So, for example, in the real case, in the case of, let's say, real numbers, we can say that the basis for the topology are the open subsets. So, if you consider open subsets in the real space, like this one, A, B, C, D, etc., then you can generate all the topology, all possible open subsets in R using those, using some of those open intervals. So, in other words, if you imagine any open subset of R, then you will find, so there exists a family of sets which are intervals, open intervals, such that O equals the sum of U lambda. Yeah, so that's the formal definition, yeah? But the intuition is simple, that you have a set which is a basis, and which means that every other open set can be realized as a sum of elements from this basis. So it's like a specific set of pieces that enables you to create anything you want. And it's enough. This set is enough to create all open subs, all open sets. And if we want to define the topology in the Cartesian product of topological spaces, we introduce this definition of topology of this Cartesian product by saying what is the basis of this topology. So imagine we have x times y, which is Cartesian product of topological spaces. Then B, like a family, it is a family of sets of the following shape, yeah. This is the basis of the topology. Okay, so we define the topology in Cartesian product by writing an explicit set of which forms a basis for this topology. To draw a picture, maybe I can write here, right? Is it? No, it's permanent mark here. No. Okay. Okay, I will draw a picture here. So, how to see that? Let's say this is a Cartesian product. Okay, we have a set, the topological space X here, and the topological space Y here. Yeah? And we want to see how do open sets look like in this product. So what we do the following thing. We choose an open set here. Let's say this open set looks like this. And we choose an open set here. Let's say it looks like this. And then we see how looks the Cartesian product of those two sets. And it looks the following way. Actually, this should be not solid. It's like open. And this is how this is an illustration how an open set in this product looks like. So actually, it's a product of open sets. In a finite example, it's pretty simple. And sets of this type, so another one would be pictured like this. We have another one here, let's say. Yeah, and if we have sets like this and we add them together, we get everything. So we get every open set in the Cartesian product can be presented as a sum of sets of this type. Okay? Do you have any questions? Is it clear?
Could you show us the previous page?
Yeah.
What is B?
What is B? B is a basis. Okay? Basis of topology. Yeah, it's written here. It's written here. That's the definition of the basis. Basis of topology in this Cartesian product. So in other words, every open set in the Cartesian product of those topological spaces is defined as a sum of elements from this space. So now you see that we have many different ways in which we can generate new topological spaces having old ones. So first of all, if we have a topological space, we can generate new topological spaces as the subspaces of the initial one. Secondly, if we have two topological spaces, we can add them together and we will get a new topological space. The third way is by dividing them in a Cartesian way. Not dividing, by multiplying them in a Cartesian way. So we take two topological spaces and we define the Cartesian product of those topological spaces. And then in this way we can complicate things, because we can, for example, take the Cartesian product and then the subspace of the Cartesian product may be summed with another space, etc., etc. And we can create very complicated, very complex topological spaces.